Overview of core.async. Core.async provides facilities for managing asynchronous programming and communication in Clojure and Clojure script. It enables the use of channels for communication between different parts of a program, allowing for more readable and maintainable asynchronous code. Core.async's approach lets you write code that looks synchronous while performing asynchronous tasks by use of Go blocks and channels. In this example, we first require the core.async library. Then, we create a channel C, which will be used for communication. Using Go blocks, one sends a message hello core.async into the channel C with the key operator. Another Go block takes the message out of the channel with the operator and prints it. This showcases basic sending and receiving messages through channels in core.async, an essential operation for asynchronous programming. Comparing core.async with other concurrency models. In the world of concurrency, various models attempt to solve the problem of performing multiple tasks at once, or in an interleaved manner. Among these, core.async, a concurrency library for Clojure, offers a unique approach by using channels as the primary means of communication between concurrent processes. Let's compare this model to traditional multithreading to highlight its uniqueness. Traditional multithreading, as seen in the first example, involves creating a new thread and executing code within it. This model is pervasive but can lead to complex issues like race conditions and deadlocks. Conversely, core.async uses channels and the Go macro for concurrency, represented in the second example. Channels act as queues that can be used to pass messages between different parts of an application, effectively decoupling the producers of data from the consumers. This model simplifies concurrency by avoiding direct manipulation of threads and focusing on the flow of data, making it easier to reason about and reducing the likelihood of concurrency-related bugs. Setting up the core.async environment. To start working with core.async in Clojure projects, you need to include it as a dependency. Core.async is a Clojure library that allows you to write asynchronous and concurrent code in a straightforward manner. We'll first add the core.async library to a Clojure project by updating the project.clj file for LineEngine or the deps.edn for Clojure CLI tools. The code snippets provided show how to include the core.async library in your Clojure project depending on the build tool you use. For LineEngine, the dependency is added under the dependencies vector in project.clj. For projects using the Clojure CLI, the dependency is specified in deps.edn. The version number 1.3.610 should be replaced with the latest version of core.async available. Including core.async as a dependency enables you to leverage its powerful APIs for managing concurrency with channels, Go blocks, and more, thus setting the stage for developing non-blocking, concurrent applications. Understanding the Clojure concurrency landscape. Clojure is a dynamic, general-purpose programming language that supports interactive development. Concurrency in Clojure is handled in a unique and powerful way, with core.async playing a pivotal role in asynchronous programming. Core.async introduces the concept of channels, providing a model for communication that simplifies concurrent programming by decoupling producers from consumers. In this Clojure code snippet, we introduce core.async and demonstrate basic channel operation. First, we require the core.async library. We then create a channel C using async chan. Using async Go blocks, we simulate a producer and consumer pattern. The producer sends a message to the channel with async, while the consumer waits to receive this message with async let, and then prints it. This highlights the core concept of core.async, where channels serve as conduits for values between independently executing blocks, facilitating communication and synchronization without direct thread manipulation. Introduction to channels. In Clojure's core.async library, channels are conduits through which data flows. They serve as a medium for communication between different parts of a program, potentially running in separate threads. This introduction aims to familiarize you with the basics of creating and using channels. This code snippet demonstrates the creation of a channel using chan and the basic operations of sending to and receiving from. A channel within Go blocks. Go blocks are used here to facilitate asynchronous operations. The can operator sends the string hello channel into the channel C, and layer is used to take a value out of the channel, which is then printed to the console. This illustrates how channels can be used to pass data asynchronously between different parts of a program. Creating channels with Chan. In Clojure's core.async library, channels are conduits through which values can be communicated between different parts of a program. A basic channel can be created using the Chan function. This function can also accept an optional buffer argument, which defines how the channel handles the accumulation of values that have not yet been consumed. Let's explore how to create a simple, unbuffered channel, and then a buffered channel. In the code above, two channels are created using the Chan function. The first example creates an unbuffered channel. Unbuffered channels do not have any capacity to hold values. A value must be taken from the channel as soon as it's put in, leading to a direct handoff between the producer and the consumer. The second example creates a buffered channel specified by buffer 10. This channel can hold up to 10 values before blocking any further put operations. Producers can continue to add values to the channel until its buffer is full, and consumers can take values from the channel, potentially emptying the buffer. Buffered versus unbuffered channels. In Clojure's core.async, channels can be either buffered or unbuffered. Buffered channels have a defined capacity that allows them to store a certain number of values before blocking. This is useful for controlling the flow of data. In contrast, unbuffered channels, zero buffer size, block the sender until a receiver is ready to take the value, facilitating direct handoff and ensuring synchronization between sender and receiver. In the provided code, two channels are created: buffered Chan with a buffer size of 3 and unbuffered Chan without specifying a buffer size, making it unbuffered. Using Go blocks, we attempt to send the value 42 to both channels. For buffered Chan, this operation succeeds immediately because the channel can hold up to 3 values before it blocks. For unbuffered Chan, the sender will block until there's a receiver ready to take the value. This is demonstrated when both values are later printed, both sends complete, but the semantics of how they wait differ based on the channel type. Closing channels. In core.async, channels can be closed to indicate that no more values will be put onto the channel. Closing a channel is a crucial aspect because it allows consumers of the channel to know when there are no more items to be processed. Let's consider an example where we first create a channel, then close it, and finally attempt to take a value from it to understand what happens in such scenarios. In this example, a channel CH is created and immediately closed using close. The Go block attempts to take a value from the channel. Since the channel is closed and contains no items, the take operation immediately returns nil, which is printed out. This demonstrates how closing a channel signals that no more data can be taken from it, which is essential for coordinating the termination of channel consumers in concurrent applications. Blocking and non-blocking channel operations. In Clojure's core.async, channels are used for communication between different parts of a program, allowing values to be passed asynchronously. Operations on channels can be either blocking or non-blocking, affecting how data is sent or received. Blocking operations wait until the operation can be completed, while non-blocking operations can immediately return with a status indicating whether the operation was successful. In this example, and illustrate blocking operations for putting and taking from a channel, where the thread will block until these operations can proceed. Conversely, and with within a Go block demonstrate non-blocking operations, which do not block the thread but instead yield control back to the Go block's scheduler. This allows other operations to be performed while waiting for the channel operation to complete. The key difference is that blocking operations can halt the progress of a program, while non-blocking operations allow for more fluid execution and concurrency management. Timeouts with alts and timeout. In Clojure's core.async library, managing operations based on time is crucial for handling asynchronous tasks efficiently. Specifically, when working with multiple asynchronous operations, deciding to proceed with whichever completes first, including a possibility that none completes before a timeout, becomes essential. This is where alts combined with timeout channels come into play, allowing us to elegantly handle such scenarios. In the example, two timeout channels are created: slow, with a delay of 1000 milliseconds, and fast, with a delay of 100 milliseconds. Using alts, we await completion of either slow or fast. Because fast will time out first, the alts call resolves with the fast channel's result. The result contains a tuple with two elements: the value received, which is nil for timeout channels, and the channel from which the value was received. This illustrates how alts, combined with timeout channels, can be used to implement logic that proceeds with whichever operation completes first, even implementing a timeout mechanism where an operation proceeds only if it's completed within a specified time frame. Transducers in channels. In core.async, channels can leverage Clojure transducers to process data as it moves through the channel. Transducers allow you to define a composable pipeline of transformation functions that do not create intermediate collections, which is especially beneficial for performance when processing streams of data. You attach a transducer to a channel during its creation. This example demonstrates how to create a channel with a transducer that doubles each incoming number. The code showcases a core.async channel using transducers to process its data. A transducer, created with map haber to 2%, doubles each number passed through the channel. The channel is created with chan10xf, where 10 defines the buffer size, and xf is the transducer. In the asynchronous blocks initiated with go, then places a number into the channel and takes a number out. Since every number passing through the channel is processed by the transducer, we put 4 into the channel and take out 8, demonstrating how the data is transformed asynchronously as it moves through the channel. Error handling in channels. Error handling in channels is crucial for maintaining a robust and resilient application. Unlike traditional try-catch blocks, channels rely on patterns such as special error values, separate error channels, or wrapping data in data structures that represent either success or failure states. Here, we'll demonstrate a common approach using a wrapper object to indicate success or error states. In the provided code snippet, we set up a simple channel sesh using the chan function. A go block is used to simulate an operation that might result in success or failure. Inside the go block, a try-catch block encapsulates an operation that might throw an exception, e.g., throw exception, error occurred, for demonstration purposes. If an error occurs, we catch the exception and pass an error object through the channel, indicating the status and error details. Conversely, if the operation succeeds, determined by your business logic, here simplified as when true, a success message is sent through the channel. After this asynchronous operation, another go block reads from the channel and checks the status of the result. Depending on the status, it either prints an error message or a success message. This pattern allows for flexible error handling in asynchronous channel operations. Reading from channels with hahaith. In core.async, a Clojure library designed for asynchronous programming, the dan operator is used to read a value from a channel in a context where blocking is allowed. This is typically done within a go block, which allows for asynchronous operations. Understanding how to properly utilize is crucial for effective asynchronous programming, as it enables the retrieval of values emitted to a channel, allowing for sequential logic that waits for asynchronous operations to complete. In this example, we first import relevant functions from the clojure.core.async library. We then create a channel C using the chan function. Next, we demonstrate sending and receiving operations using a go block. In the first go block, we use the det operator to send the string hello world into the channel C. In the second go block, we use the peck operator to read the value from the channel C and print it to the console. The test operator allows the go block to pause execution until a value is available on the channel, making it suitable for handling asynchronous data flows. This example showcases a basic use case of utilizing channels for communication between asynchronous blocks of code. Writing to channels with the d operator in core.async is used to write a value to a channel in a Clojure async environment. This operation is non-blocking, but requires being used within a go block, as it yields control back to the scheduler, allowing other operations to run until the channel is ready to accept the value. This approach helps in efficiently managing concurrency without locking. Here's a simple example demonstrating how to use channer to send a value to a channel. In this code snippet, we first import required functions from Clojure.core.async. We then create a new channel C using the chan function. Inside a Go block, we use jed to attempt to send the value 42 into the channel C. The Go block ensures that this operation is non-blocking and can yield execution if the channel is not ready to receive the value. This is particularly useful in scenarios where you want to write to a channel without stopping the execution of the program, enabling more sophisticated concurrency patterns. The alts operation. In Clojure's core.async, the alts function is a powerful operation which allows a program to wait on multiple channels simultaneously and proceed with the first one that becomes available. This versatility makes it an essential tool in concurrent programming, enabling tasks to be coordinated without rigid sequencing, hence increasing efficiency. Here's a basic example demonstrating its usage. In this example, two channels CH1 and CH2 are created. Messages are asynchronously sent to both channels. The alts operation within a separate Go block is then used to listen on both channels. It waits for a message to become available on either CH1 or CH2. Once one of them has a message, alts returns a vector containing the message, in this case, either message from CH1 or message from CH2, and the channel from which the message was received. This allows the program to act based upon whichever message is received first, demonstrating a non-deterministic way of communication between concurrent processes. Pipeline processing with pipeline, pipeline blocking, and pipeline async. Core.async provides a powerful abstraction for streamlining processing of data through stages, which can be achieved using pipeline, pipeline blocking, and pipeline async. These three functions are essential for efficient processing of sequences of data asynchronously, allowing the construction of complex processing pipelines with ease. Let's examine how each of these functions works. The pipeline function processes items from in-chan, applying a transducing operation, here, incrementing each item, and places the results into out-chan, using 4 concurrent workers. Pipeline blocking is similar, but is used for operations that may block, ensuring they don't interfere with the async system. Lastly, pipeline async allows for asynchronous processing of each item, using a provided function that takes an item and a channel to which the processed result is pushed. This example demonstrates how to increment each item asynchronously and push it to out-chan. All these operations help in efficiently managing data flow, offering both synchronous and asynchronous capabilities. Mult and tap for pub/sub models. In Clojure's core.async library, mult and tap functions are utilized to implement the publisher-subscriber pattern. Here, mult takes a channel and returns a mult icast channel. Multiple subscribers can tap into this multicast channel. When a message is put onto this multicast channel, it's dispatched to all tapped subscribers. This model enables a one-to-many dissemination of information where messages are not consumed, removed, by reading. In the provided code, C is a channel created using chan. M is a multicast channel derived from C via mult. We then tap two subscribers, sub1 and sub2, into M. Each subscriber is associated with its own channel. A Go block is used to asynchronously put a message onto C. Given that M is a multicast channel, both sub1 and sub2 receive the message. The println statements enable us to see the message dispatched to each subscriber. This showcases how mult and tap can facilitate a pub/sub communication pattern. Merging multiple channels with merge. In the context of concurrent programming with core.async in Clojure, merging multiple channels is a technique that allows us to consolidate data from several input channels into a single output channel. This can be extremely useful when you have multiple asynchronous processes running and you need a unified way to handle their outputs. The merge function in core.async facilitates this process. In this code snippet, we're using Clojure's core.async library to demonstrate merging channels. We start by requiring the library. We then define two channels, CH1 and CH2, for simulating two separate sources of data. The merge function is used to combine these channels into a new channel, smurged. Through Go blocks, we simulate sending data to CH1 and CH2. The merged channel, CH-merged, will receive data from both H1 and CH2. Lastly, a Go loop is used to continuously read from CH-merged and print the output, demonstrating how data from both channels can be processed in a unified manner. Splitting a channel's values with split. The split function is a crucial tool in Clojure's core.async library, allowing for the division of a single input channel into two separate output channels based on a predicate function. This operation facilitates the processing of different types of data concurrently, exemplified by dividing numbers into evens and odds. This code showcases the use of split in action. It initiates with requiring necessary functions from core.async, followed by creating an input channel. The split function is called with this input channel and a predicate function, even, which tests if a number is even. It returns two channels, evens for even numbers and odds for odd numbers. A simple processing function, process, is defined to continuously read from these output channels and print the results. Finally, numbers 2 and 3 are put into the input channel and process function is invoked. This demonstrates how values entering the input channel are directed to the appropriate output channels based on their parity, thereby splitting the channel's values. Understanding the role of AND within Go blocks. In the Clojure core.async library, Go blocks allow for asynchronous code execution. Within these blocks, the read and write operations are used to facilitate communication through channels. Let's explore how they work together to enable concurrent programming patterns. In the provided code, a channel CH is created using chan. Inside a Go block, chetchesh writes the string hello core.async to this channel. Another Go block is used to read from CH using thech and prints the received message. Finally, close.ch closes the channel. This demonstrates how and get are used within Go blocks for asynchronous communication between different parts of the code. Introduction to Go blocks. Go blocks are a cornerstone of asynchronous programming in Clojure, allowing you to write non-blocking code that looks synchronous. They facilitate communication between different parts of your application without tying up threads, making your program more efficient and responsive. In this snippet, we introduce a simple example of using Go blocks with Clojure's core.async library. A channel C is created using the chan function. The Go macro spawns asynchronous blocks. In the first block, the number 42 is placed onto the channel C with the bedog operator, which denotes an asynchronous put operation. The second Go block waits for a value from C using the ed operator, indicating an asynchronous take. Once a value is taken from the channel, it is printed to the console. This demonstrates how Go blocks can coordinate simple asynchronous tasks like sending and receiving values through channels without blocking the program's execution. Under the hood, how Go blocks work. To understand how Go blocks work in Clojure's core.async library, it's important to peel back the layers and scrutinize the mechanics involved. Essentially, Go blocks automate state machine creation from sequential code, making asynchronous programming more intuitive. This automation handles the coordination of channel operations, e.g., take, put, without blocking threads, utilizing a lightweight concurrency model. In this code example, Go creates a state machine around the channel operation. Instead of blocking, as it would in a synchronous operation, the that operator within a Go block yields control back to the scheduler, allowing other operations to proceed. Once the channel has a value to take, control is returned to the code following the bear inside the Go block, with that value ready for use. This conversion of sequential code into a state machine enables the non-blocking coordination of concurrent operations, leveraging Clojure's powerful concurrency primitives without immersing the developer in the complexity of managing threads directly. Using Go blocks for non-blocking concurrent programming. Go blocks are a core concept in Clojure's core.async library, allowing for concurrent programming that is both efficient and easy to reason about. They enable non-blocking asynchronous operations by leveraging lightweight threads. Within a Go block, channels are used for communication between concurrent tasks, without the complications of traditional locking mechanisms. This example demonstrates the use of Go blocks to perform concurrent operations. In this code, require is used to include the core.async library, specifically the go, chan, and constructs. A channel C is created with the chan function, which facilitates communication between Go blocks. Two Go blocks are declared. The first one sends a message, hello from Go block, into the channel C using the un operator, and the second one waits to receive a message from C with the YAL operator, printing the message to the console once it's received. This demonstrates how Go blocks can be used for non-blocking communication between separate concurrent operations. Limitations and best practices with Go blocks. Go blocks allow for asynchronous programming in Clojure, enabling non-blocking operations and concurrent task management. While powerful, they come with limitations and require adherence to certain best practices for optimal functionality. In the provided code, a Go block is used for asynchronous data processing. A few key points to understand. 1. Blocking operations. Go blocks should not contain blocking operations as they are executed in a finite set of threads. Use non-blocking counterparts like instead. 2. Error handling. Errors in Go blocks can lead to silent failures. Ensure you have mechanisms, e.g. try-catch blocks for error handling. 3. Looping constructs. Infinite loops within Go blocks can monopolize thread pool resources. Use them judiciously. 4. Resource management. Since Go blocks share thread resources, it's crucial to avoid long-running operations within them to prevent thread starvation. Following these practices ensures that your asynchronous operations are efficient, safe, and responsive. Using core.async in web applications. Core.async provides a powerful toolset for managing asynchronous operations in web applications, especially in the context of AJAX calls or handling complex user interactions. Below is a basic example demonstrating how to perform an AJAX request using core.async channels, optimizing for readability and ease of use. In this code snippet, we first import necessary namespaces, including cljs.core.async for core.async functionalities, and cljs.htp.client for making HTTP requests. We then define a Clojure script Go block that performs an asynchronous HTTP GET request to a specified URL. Inside this Go block, the add operator is used to wait for the response from the HTTP request without blocking. Based on the response, we use the put function to send the response body to my channel if the request was successful, or the status code to error channel in case of failure. This pattern demonstrates the clean separation of asynchronous operations and error handling, maintaining code readability and simplicity. State management with channels. In core.async, channels can be used for more than just passing messages between Go blocks or threads. They can also serve as a means of managing state within an application. By funneling all modifications to a particular piece of state through a channel, you can ensure that state changes are handled in an orderly and predictable fashion. This technique also encapsulates state changes, making your application's logic easier to follow. Let's explore how this can be accomplished through a simple counter example. In this code snippet, we define a channel named counterChan for managing the state of a counter. The Go loop block listens for messages on counterChan. Each message is expected to be an integer that represents how much to adjust the counter by. Inside the loop, it waits for a value from the channel using cache, then increments or decrements the counter based on the received value. This approach centralizes state updates and makes them explicit and asynchronous. By placing state changes on a channel, we can easily adjust, monitor, or extend how state adjustments are made, leading to a more maintainable and flexible architecture. Furthermore, this pattern aids in keeping functions pure by isolating side effects. Building complex pipeline transformations. In this section, we focus on constructing intricate pipeline transformations using core.async channels in Clojure. Pipelines allow for the sequential processing of data through a series of stages, where each stage might perform computations, filtering, or transformations. We'll explore how to build these pipelines to handle complex data flows effectively. This code creates a simple pipeline for data transformation with pipeline. The pipeline function is used to process items from the input CHAN channel, transform them according to the xform transformation function, which in this case doubles the values and simulates some processing time with thread sleep, and then pass them onto the output channel. The number 4 specifies the number of concurrent workers processing items from the input to the output channel. The go block is used to simulate pushing 2 items, 1 and 2, into the input chan. The transformed items are then fetched from output chan and printed out. This demonstrates how pipelines can be used to manage and apply complex transformations to streaming data in a concurrent manner. Integration with external systems and APIs. Integrating core.async with external systems and APIs often involves performing I/O operations such as HTTP requests, which are inherently asynchronous. In Clojure, core.async channels provide a powerful abstraction for handling such asynchronous tasks by decoupling the operation initiation from its completion and result handling. Below is an example demonstrating how to integrate a simple HTTP request within a core.async flow. In this example, we define a fetch URL function that initiates an HTTP GET request to a specified URL using the CLJ http.client/get function. We create a core.async channel, response chan, which is used to convey the HTTP response back to the caller. Inside a go block, we perform the actual HTTP request asynchronously. Once the request completes, we use async/ to place the response onto response chan. The caller of fetch URL can use another go block and async to read the response off the channel once it's available, thus integrating with an external API in a non-blocking manner. This pattern allows for clean, readable code that gracefully handles the asynchronous nature of I/O operations. Performance optimization and monitoring. In the context of core.async, performance optimization and monitoring involve techniques to ensure your asynchronous operations run efficiently and provide visibility into their behavior. This can include optimizing the size of your channels, using transducers to reduce overhead, and monitoring the throughput and latency of operations. Here, we'll explore a simple pattern to monitor the processing time of tasks in a pipeline. In the provided code, we create 2 channels input and output, with output being augmented with a transducer that simulates a task taking 100 milliseconds. We use start time to capture the start time of the operation. The go loop reads values from the input channel, forwards them to the output channel, and then logs the elapsed time since start time. This simple pattern allows tracking the processing time of tasks as they go through the system, illustrating a fundamental technique for performance monitoring in asynchronous operations. Debugging core.async code. Debugging core.async code can be challenging due to the nature of asynchronous operations and concurrency. However, understanding a few key concepts and utilizing some strategies can significantly aid in this process. One useful method is to tap into channels to inspect the values passing through without affecting the flow of the program. The tapchan function demonstrates a simple yet effective debugging technique for core async code. It takes a channel, chi, and returns a new channel, tap. Inside a go loop, it continuously takes values from the input channel, prints these values to provide visibility into what is passing through the channel at any point, useful for debugging, and then puts the values onto the tap channel. This allows the flow of data to be observed without interruption. By injecting tapchan at points of interest in your async flow, you can gain insights into the data moving through your channels and potentially identify where things might not be working as expected. This technique is non-invasive and maintains the integrity of your data flow. Case studies of core.async in production. In a real-time data processing system, core.async enables efficient handling of live data streams. This example demonstrates a simplified version of processing real-time market data, where each piece of data is processed asynchronously as it arrives. This code showcases the use of channels and go blocks for asynchronous data flow. A data channel is defined to capture incoming live data. The processor channel applies a transformation through process data function asynchronously. 2 go loop instances are defined, one for reading data from data channel and pushing it to processor channel, another for processing data from processor channel and performing an action, in this case, print. This pattern allows for efficient, non-blocking data processing. Complementary libraries for core.async. In the realm of Clojure's core.async, several complementary libraries enhance its functionality or make it easier to work with. These libraries offer additional utilities, patterns, or integrations with other Clojure libraries or Java frameworks, making core.async even more powerful and flexible. While core.async provides the foundational primitives for asynchronous programming in Clojure, such as channels and Go blocks, there are times when additional functionality is desired. Complementary libraries can provide features like more complex channel operations, integration with web frameworks, improved error handling, or debugging tools. They help in developing more comprehensible and less boilerplate asynchronous code, or in integrating core.async into larger applications. Examples include Manifold for stream-centric programming, Aleph for asynchronous communication, and core.async pipeline utilities for processing streams of data. These libraries are not part of core.async, but are designed to work seamlessly with it. Testing tools for core.async code. Testing asynchronous code can be challenging due to its non-linear execution flow. In the context of Clojure and core.async, there are strategies to effectively test asynchronous code to ensure reliability and correctness. Let's explore a simple test routine using Clojure.test and core.async, illustrating how to test a core async process. In this example, we define a test case async test using def-test from the Clojure.test library. The test essentially checks if an asynchronous process, simulated with a timeout, completes as expected. A channel outchan is created and used to communicate the completion of the process. The Go block waits for 100 milliseconds, simulating an asynchronous task, and then sends a done message through outchan. The is macro checks if the value received from outchan equals done, thereby asserting the correctness of the asynchronous process. This approach helps in writing tests for more complex asynchronous behaviors in core.async. Visualization tools for debugging. Debugging concurrent applications can be challenging due to the non-deterministic nature of asynchronous operations. Visualization tools play a crucial role in simplifying this task by providing a graphical representation of the program's execution flow. These tools can help identify bottlenecks, deadlocks, and other concurrency-related issues. In this example, we'll discuss a hypothetical async viz tool designed to integrate with core.async for Clojure. In the snippet above, asyncviz.core/enable is a fictional function to activate the visualization feature of the async viz tool. The go loop expression represents a basic asynchronous loop where a message is printed every 1000 milliseconds. The GOR operator is used to retrieve values from a channel, in this case, a timeout channel that unblocks after 1000 milliseconds. With async viz, developers could visualize when each println occurs relative to the channel operations, providing insights into the asynchronous flow and facilitating debugging. Integrating with Clojure script. Integrating core.async with Clojure script enables handling asynchronous programming in a seamless way, particularly useful for event handling and AJAX requests in web applications. Below is a simple example demonstrating how to use a core.async channel in a Clojure script application to perform an async AJAX request. In this code snippet, we start by requiring the necessary namespaces, including clj.http.client for making HTTP requests and cljs.core.async for async operations. We then initiate a Go block, which allows us to use take and put operations on channels in a non-blocking way. Inside the Go block, we make a GET request to a hypothetical API and wait for the response asynchronously using the he operator on the HTTP request's return value, which is a channel. Finally, depending on the success of the request, indicated by the success key in the response, we display an alert to the user. This example shows core.async's power to simplify handling asynchronous operations like AJAX requests in Clojure script. WebSocket communication with core.async. WebSockets provide a way for web clients and servers to communicate over a persistent connection, allowing for full duplex, bidirectional communication. By leveraging core.async, we can effectively manage these communication channels in a Clojure script application, providing a more responsive and interactive user experience. The following example demonstrates how to set up a basic WebSocket connection and use core.async channels to handle messages. This code snippet begins by defining a Clojure script atom WS to hold the WebSocket instance. The function init_WebSocket initializes the WebSocket connection using the provided URL. Within this function, two core.async channels, incoming and outgoing, are created to handle the flow of messages. The WebSocket's onMessage event is set up to put any incoming message into the incoming channel. Concurrently, a go loop continuously takes messages from the outgoing channel and sends them through the WebSocket connection. The return value of init_WebSocket is a map containing both channels, allowing the calling code to interact with them to send or receive messages. Event handling in GUI applications. In GUI, graphical user interface applications, event handling is crucial for responding to user interactions, such as clicks, key presses, and mouse movements. Using core.async, we can manage these events asynchronously, improving the responsiveness and maintainability of the application. Below is a basic example in Clojure script showcasing how to use core.async channels for event handling in a GUI application. This code snippet demonstrates how to use core.async for event handling within a GUI application written in Clojure script. Firstly, a channel named event_chan is created to capture and queue events. Using add_event_listener, we specify that on every click event within the document, the clicked event object is put into event_chan. The go-loop construct listens for these events asynchronously. Whenever an event is taken from the channel, the code to process this event, in this instance simply printing the event to the console, is executed. This approach allows handling GUI events asynchronously, enabling non-blocking UI logic and smoother user interaction handling. Concurrent data processing pipelines. In this example, we'll build a concurrent data processing pipeline using Clojure's core.async library. The pipeline will consist of 3 stages: input collection, processing, and output. Each stage will be connected by channels, allowing for asynchronous communication between stages. This setup is ideal for scenarios where data needs to be processed in stages and can benefit from concurrency, such as in data transformation tasks or real-time data analysis. The code snippet creates a simple concurrent data processing pipeline with 3 stages: input collection, processing, and output. Input, processed, and output are channels that serve as the conduit for data through each stage. The processing stage is a go block that reads from the input channel, transforms the data by prefixing it with processed, and then sends it to the processed channel. The pipeline blocking function takes the processed data, further transforms it by prefixing output through a map operation, and then forwards it to the output channel. This stage uses 2 threads to concurrently process messages. Another go block is set up to continuously read from the output channel and print the results. Finally, the doTimes loop simulates input by sending data to the input channel, and close is called on input to indicate no more data will be sent. Implementing reactive systems. Reactive systems are responsive, resilient, elastic, and message-driven. They react to changes in the environment, user inputs, or other systems. In Clojure, core.async provides a powerful model to implement such systems by decoupling components and allowing them to communicate asynchronously through channels. Let's consider a simple reactive system where a sensor periodically broadcasts temperature readings to be processed and displayed. This code demonstrates a basic reactive system with 2 asynchronous process loops. One simulates a temperature sensor emitting readings, and the other represents a display device. Sensor output and display input are channels with buffers of size 100, ensuring that our processes don't block each other due to a full channel. The sensor process uses async go loop to continuously generate and send new readings to the sensor output channel, simulating sensor data broadcasting. On the other side, the display process waits for readings from the display input channel and prints them out, simulating a reactive display. The last async go block continuously takes readings from the sensor output channel and puts them on the display input channel, linking the 2 processes. This exemplifies core.async's capability to manage asynchronous data flows, making it a viable tool for building reactive systems. Core.async in distributed systems. In distributed systems, Clojure's core.async offers a model for handling concurrent operations across multiple systems, which can lead to more efficient data processing and communication. We'll explore how to use channels and Go blocks to manage asynchronous tasks in a simulated distributed environment. This example simulates a simple distributed system where 3 core.async processes, represented as Go blocks, communicate through channels. The first process sends a message through CH1. The second process takes the message from CH1, processes it, simulated by adding processed to the message, and then sends it to CH3 through CH2. The third process receives the processed message from CH2 and prints it out. This demonstrates how core.async can be used to manage data flow and task execution in a distributed system.